Hello everyone, myself Vinay Kumar. Today we are going to learn about the various types of windings. In the previous period, we have already discussed about the methods of dynamically induced EMF and Fleming's right hand rule. In this, various fingers represent there is nothing but the forefinger, middle finger, and thumb represents the magnetic flux, the current direction, and the rotation of the conductor. It is direction of rotation of the conductor, and this right hand rule is applicable to DC or AC generators. And also we have learned about the simple working principle of a simple loop, that is nothing but a single coil generator, and also the various parts. What are the various parts of the DC generator and their functions and how they work in a DC generator. We have learned all these in the previous classes. Okay, the main objective of this presentation is to know the various types of windings in generators. While knowing these various types of windings, there are certain important terms which we have to know. First, let us know the important terms used. First one is pole pitch and conductor. I will be explaining all these in the next slides. And the third one is a coil. Nothing but when two rectangular conductors become a coil. And what is coil span or coil pitch? And about full pitched coil and fractional pitched coil. And also we are going to learn about the pitch of winding. Now let us see one by one each term. The first one is back pitch. Have you ever heard about this term back pitch? I think you have not heard about this back pitch. Now let us learn this, the definition or what is meant by back pitch and front pitch, resultant pitch, commutator pitch. And first I would like to explain about the pole pitch, which is denoted by the term YP. You can see here YP. The pole pitch is defined as the distance between the two adjacent poles. Nothing but it is the distance between the two adjacent poles. And it is always equal to the number of armature conductors per pole. Let us see an example for better understanding of this term YP. Let us take an example, that is, if there are 36 conductors and 4 poles, then what's the pole pitch? Then pole pitch is given as YP is equal to Z, that is nothing but Z by P. Z is nothing but the number of conductors and P is nothing but the number of poles. Now the pole pitch YP is equal to 36 by 4. 36 conductors by 4 poles, which is nothing but the answer is 9. Here the pole pitch is 9. Now let us see the second important term, that is conductor. I think all the electrical students know about the conductor. Here in the figure A, you can see a rectangular conductor which are placed in the armature slots. The ends of this conductor is connected to the commutator segments, which here you can see in the figure A. This is the commutator and this is the rectangular coil, and here AB is the conductor and CD is another conductor. We know that a EMF will be induced in this conductor only, and this conductor, we place this conductor in a magnetic field. I already said that AB is one conductor and CD is the another conductor. Their ends are connected to the commutators. See how the rectangular coil is connected to a commutator. You can see clearly in the figure A and also in the figure B. Here AB or CD is conductors and the whole rectangular conductor is called a coil. The next important term is coil pitch, or also called as span, and it is denoted by YS. That is, coil pitch is denoted as YS. And this coil pitch is defined as the distance measured in terms of armature slides between two sides of a coil. Here the coil pitch or span for conductor A is 4. Here observe this conductor A, it is in slot 1 and the other conductor is in slot 5. Okay, now the span is 5 minus 1. Not, nothing but the span is 4. Now what will be the span for this B conductor? The first conductor is in the slot number 3 and the second conductor is in the slot number 6. So the coil span or coil pitch for conductor B is 6 minus 6 minus 3, which is equal to 3. Now let us see the other important term, that is full pitched coil. How we can define this? Full pitched coil means if a coil pitch is equal to pole pitch, the winding is called as full pitched winding. What is that? The coil pitch is equal to pole pitch. Then it is called as full pitched winding. Let us see an example. Let us consider if there are 16 conductors and 4 poles, then pole pitch is equal to the number of conductors by number of poles, that is 16 by 4. So the answer is 4. Now the pole pitch is 4 and the coil pitch. What is the coil pitch of conductor A? As I have said in the previous slide, the coil pitch is 5 minus 1, means one conductor is in the slot 1 and the other conductor is in slot 5. So the coil span is 5 minus 1, which is nothing but 4. Here from the definition we can say that the coil pitch is equal to pole pitch. Here the coil pitch is 4 and also the pole pitch is 4. So this winding is called as full pitched winding. I think now you are clear about the full pitched coil. Now let us see the next term, that is fractional pitch coil. In the previous one we have learned about full pitched coil. Now we are learning about fractional pitch coil. Fractional pitch coil, a coil is said to be fractional pitch when the coil pitch is less than the pole pitch. Okay, let us see an example. And this, in this, the coil span must be 180 electrical degrees. Let us see an example. If there are 36 slots and armature, and there are 4 poles, then the coil pitch is nothing but it is the ratio of the number of slots to the number of poles, a number of conductors to the number of poles, which is equal to 36 by 4, which is nothing but 9. And the next one is back pitch. and this back pitch is denoted by YB, and it is defined as the distance measured in terms of number of armature conductors between the two coil sides of a coil measured around the back of a armature. And let us see, the next one is front pitch, which is defined as the distance between the two coil sides connected to the same commutator segment. We can also see this front pitch YF, which is denoted by YF in the figure 3. That is these are the two coil sides. This is one coil side and this is the another coil sides connected to the same segment, same commutator segment. You can clearly see this. These two are connected to the same commutator segment. And the next important term is pitch of winding, which is denoted as Y, and this can be defined as the distance between the beginning of two consecutive turns. Here there will be two types of windings. One is lap winding and the other one is wave winding. In a lap winding, the pitch of winding Y is defined as the difference between YB and YAF. Whereas in a wave winding, it is defined as the sum of YB and YF. Now let us see the next important term, that is resultant pitch, and it is denoted by YR. Here we can see the term YR in the figure 2, and this YR is defined as the distance in terms of number of coil sides between the start of one coil. This is the start of one coil and the start of next coil to which it is connected. I think you have understood this. YR is nothing but it is the distance in terms of coil of one side and start of the next coil. This is one coil, start of one coil, and this is the start of the next coil, and the distance between these is called as resultant pitch. And let us see the next important term, that is commutator pitch. And this commutator pitch is denoted as YC. You can see this commutator pitch in the figure 3. See YC in this figure 3. And this commutator pitch is defined as the distance measured in terms of commutator segments between the segments to which the two ends of the coils are connected. Between the segments of which the two ends of a coil are connected. Now, the next important term is single layer winding. Here, the name itself indicates that it is a single layer, means there will be only one conductor in one slot. You can see in the figure 4, this circle shape one is the conductor, and this is the slot of the armature. Let us read out this. It is the winding in which one conductor or one coil side is placed in each armature slot as shown in figure below. Now, the next one is two layer winding. The name itself indicates that there will be two layers of winding in each slot, and this you can also can observe in the figures shown below. You see, this is one slot, and there are two conductors. One is a thick line and the another one is a dotted line. The thick line represents the topmost winding, and this dotted line indicates the bottom winding. You can observe here in all the slots there are only two windings per slot. In this way the armature will be, and the poles will be placed in such a fashion. There are four poles, you can clearly see this: North Pole, South Pole, and North Pole, South Pole. And the middle one, this middle one is the armature, and this circles indicates the windings, and these are the slots. In each slot there are two conductors. Okay, there are two conductors in each slot. Let us now read out this. It is the winding in which two conductors are coil sides per slot arranged in two layers. And now let us go to the next topic, that is types of windings. Mainly there will be two types of windings. One is lap winding and the other one is wave winding. Here we can see the clear pictures of lap winding and also wave winding. You can see here armature, commutator and the commutator segments. Now let us see the simplex lap winding. This simplex lap winding finishing end of one coil is connected via the commutator segment to the starting end of the adjacent coil situated under the same pole. Here the pole is same. Okay, you have to remember that one. Same pole. Commutator segments under same pole. You can see how the winding, how the lap winding will be. Now let us see a simple wave winding. In a wave winding, a coil side under one pole is connected to another coil side which approximately occupies the same position under the next pole. Here we can see this one in this diagram. One coil side of one pole is connected to the second coil side. This is the second coil side which is connected in the next commutator segment under next pole. In this fashion, the wave winding will be. You can simply say that in a rectangular coil there will be two conductors. One conductor will be connected to a commutator segment under one pole, and the second conductor will be connected to the commutator under next pole. Here the poles will be different. One direction around the armature in a series of waves as shown in the figure. Now Let us see the comparison between lap and wave winding. This question was frequently asked in various examinations. This is important even in the diploma examinations and also in your higher studies, nothing but BTech examinations. Let us see the comparison. What is the difference between these two windings? Generally, in a lap winding, the EMF which is generated will be less, whereas in a wave winding, the EMF generated will be more. And this winding, lap winding, carries high currents, and the wave winding carries low currents. In a lap winding, equalizer rings are necessary, whereas in wave windings, these rings are not necessary. The copper consumption in a lap winding is more. The winding will be more, so the copper consumption in a lap winding will be more. Whereas in a wave winding, the copper consumption is less. And the number of parallel paths is always equal to the number of poles in a lap winding. This we have already seen in the EMF equation. There we have seen as A is equal to P, where A is the number of parallel paths and P is the number of poles. And whereas in a wave winding, the number of parallel paths are always equal to 2. So there we substitute A is equal to 2, where in EMF equation. So it becomes the denominator in the EMF equation for a wave winding becomes 120. 16 to 2 is 120. And in a lap winding, the number of conductors are unrestricted. Whereas in a wave winding, these conductors are restricted. And these lap windings always carries these are suitable for low voltage high current generators, whereas the wave winding is best suited for high voltage and low current generators. And in a lap winding, the number of commutator segments is always equal to the number of slots. That is, the number of slots will be on the armature and the number of segments will be at the end of the armature, which we have already seen in the parts of a DC generator. And in a wave winding, segments is equal to number of slots. Yeah, from this presentation, we have discussed about the important terms, all the important terms, and the types of windings. That is nothing but the lap or the wave and the differences. We have already learned about the comparison between lap winding and wave winding. Let us see a small quiz. What are the types of windings in DC generators? A. Lap winding. B. Wave winding. C. Both. D. None of them. Answer is both. Depending upon the current and voltage, we can choose the type of windings. The second one is how many parallel paths are there in a lap winding? We have discussed this point in the EMF equation and also in the comparison between the wave winding and lap winding. So come on, what is the answer? Here the options are A 2, B number of poles, C both, and D none of the above. The answer is B number of poles. That is nothing but A is equal to P. A is the number of parallel paths, which is equal to P, nothing but number of poles. Let us see the next question, that is which winding is suitable for high voltage generator? This one we have discussed in the comparison between lap and wave windings. The options are A lap winding, B wave winding, C both, and D none of the above. What will be the answer? Yes, the answer is wave winding. Let us see some of the frequently asked questions in this topic, that is important terms and types of windings and the comparison. In this way, the questions will be, that is, what are the types of DC windings? Define pole pitch and coil pitch. If it is for 3 marks, then we can just write about the definitions only. That's enough. If it is for more, that is nothing but 5 or 8 marks, then we have to draw the winding diagram also. Explain wave winding and compare lap and wave winding. Comparison between the two windings. Now let us go to the next topic, that is The different types of DC generator connections. Voltage and current equations for different types of DC generators. In this presentation, we will learn some types, and in the next presentation, we will learn the others. Let us start from the classification of DC generators. DC is nothing but direct current which produce the generator which produce direct current are called as DC generators. Let us see the classification. Mainly these DC generators are classified based on their excitation. Excitation. This is classified into two types. First one is separately excited generators, means here the excitation for these generators are provided by some external source that may be a battery, means the magnetic field is produced by some batteries. And the second one is self excited DC generators. Self excited means the excitation which this generator is using produces on its own. The excitation which it is using is produced by this generator itself. So these type of generators are called as self excited generators. And these generators are further classified as further classified into three types based on the type of connection, that is nothing but the type of connection of the field type connection. Okay, let us see the classification of self excited generators. In this, the first one is shunt generator. Shunt generator means in a generally in a generator there will be three parts. One is armature, second one is field, and the third one is load. Here shunt means nothing but parallel. If the armature and field and load are connected in parallel, then such a type of generator is called as shunt generators. And the next one is series generators. In this type of generators, the armature, field, and load, all the three are connected in series. If all the three are connected in series, then such a generators are called as series generators. And the next one is compound generators. Compound generators are nothing but it is the combination of both the types of generators. Nothing but shunt generator, shunt type connection, and also there will be series type of connection. The circuit diagram for all these three types will be seeing in the next presentation, and these compound generators are further classified into two types. One is long shunt DC generator. Long shunt DC generators. Here the whole field winding, shunt field winding will be connected in parallel to the both, that is armature and series winding. Okay, I'm once again repeating. The shunt field winding is connected in parallel with armature and field. Then such a type of generators are called as long shunt generators. And the other type is short shunt generators. Short shunt generator means the shunt field here is connected in parallel to the armature only. If the, I am repeating once again, if the shunt field winding is connected in parallel to the armature, then such a type of DC generators are called as short shunt generators. Okay, and the circuit diagrams, the voltage and current equations, and the various currents and voltages in the circuit I will be showing in the next slides, that is in the next PowerPoint presentation. Today, up to this, we'll make an end. Okay, bye.